You ever look at a huge bridge or a skyscraper and just wonder how it doesn't all come crashing down? Well, the secret is something called statics. It's basically the science of things that don't move. And it's all about this invisible, perfectly balanced battle of forces happening all around us. Today, we're going to pull back the curtain on the system engineers use to make sure they win that battle every single time.
I mean, look at this thing. It's not just a bunch of metal beams, right? It's a really complex puzzle of pushes and pulls. Every single one of those pieces is under some kind of stress, and the only reason the whole thing works is because all those hidden forces are in perfect balance. You get one little calculation wrong, well, the results can be absolutely catastrophic.
So, yeah, that's the million-dollar question, isn't it? When we're looking at a structure like this truss, and you've got forces pushing and pulling on it from all over, how in the world do you figure out what's really going on inside each one of those beams? How do we actually put a number on those forces to know for sure that the design is safe?
Okay, I know what you're thinking. This looks like you need to be some kind of genius to figure it out. But here's the secret. It's not about some flash of brilliance. Not at all. The key is having a system. A repeatable, reliable process that lets you take all this chaos and turn it into something orderly and solvable.
So let's get right into it. We're calling it the Statics Master Method. And it's a simple 8-step guide that you can use for pretty much any statics problem you'll ever face. It's a really solid process that guides you from a confusing mess of a problem straight to a clear, correct answer.
The first 4 steps, this is all about setting up the problem correctly. And honestly, this is where the real engineering magic happens. First up, you just restate the problem. Sounds simple, but it makes sure you know exactly what you're trying to find. Second, and this is the big one, you draw a free body diagram. Seriously, this is the most critical step. It's how you make all those invisible forces visible. Third, you list out the fundamental rules of the game, the laws of physics that always apply. And fourth, you write out your equations using symbols only. No numbers yet. This is a total pro move because it lets you check your logic before any numbers can trip you up. Okay, now we can finally talk about numbers. So in step 5, you plug in your values and you always include the units. Step 6 is just, well, it's the algebra part. You just solve. But wait, you're not done. Step 7 is the professional sanity check. You ask yourself, do my units even make sense? You know, if you're looking for a force and you get an answer in kilograms, something's gone wrong. And do the forces actually balance out? This is how you prove to yourself that your answer is right. And finally, step 8, you just summarize everything nice and clearly. It's the whole package.
And really, that's the whole idea here. You take a big, scary problem and you just break it down into these little, manageable pieces. You don't worry about the end, you just focus on the step you're on right now. It's like the saying goes, one step at a time, you'll get there. It really is that simple.
All right, that's enough talk. Let's see this thing in action. What do you say? We're going to take the master method and throw it at a classic truss problem. Let's watch how it takes something that looks complicated and turns it into a straightforward, step-by-step solution. Okay, step 1. Restate the problem. What are we trying to do? We need to find the force in every single member of this truss. And what do we know? We've got 2 loads acting on it. P1 is 800 newtons pulling down, and P2 is 400 newtons pulling to the right. Simple. The goal is crystal clear. Now, before we jump into step 2, we have to talk about this for a second. The free body diagram, or FBD. I'm telling you, if you can get good at this one thing, you've basically mastered statics. The whole idea is to take your object, in this case the truss, and just isolate it in space. You get rid of all the supports and connections, and you replace them with the forces they're creating. It's how you make the invisible visible.
So for our truss, let's do it. We draw the truss all by itself. Now that pin connection at point A, a pin can stop something from moving left, right, and up and down. So we replace it with 2 forces, an AX and an AY. Over at C, that's a roller. A roller only stops up-down motion, so we only need one force there, an upward one we'll call CY. Then we just add the forces we already know, P1 and P2, and boom! We've just turned a real-world object into a diagram we can actually solve.
Step 3. What are the rules of the game? Well, for anything to be standing still, in static equilibrium, 3 things have to be true. All the forces going left and right have to cancel out to 0. All the forces going up and down have to cancel out to 0. And all the twisting forces, the moments, they also have to cancel out to 0. Basically, no sliding, no lifting, and no spinning. These 3 rules are our main tool. All right, Now for some real strategy. This is where we combine steps 4 and 5. Watch this little trick. We're going to sum up all the twisting forces, the moments, around point A. Now, why point A? Think about it. The two forces we don't know, AX and AY, are acting right at point A. That means they have zero twisting effect there. So by picking that point, we just made two of our unknowns disappear from the equation. It's a classic shortcut that leaves us with a super simple equation where CY is the only thing we don't know. Brilliant, right?
And now, step 6, we solve. We just do the math. From that moment equation, a little bit of algebra tells us that CY is 514 newtons. Cool. Now that we have that, we can plug it back into our up and down force equation. That tells us AY has to be 286 newtons. And finally, the left-right equation is super easy. It shows us that AX is negative 400 newtons. And don't let that negative sign scare you. All it means is that the force is actually pointing in the opposite direction from what we guessed. And just like that, 1, 2, 3, all the external forces are solved.
So that's the outside forces. But what about the forces inside the beams? For that, we use another clever convention. When we look at each joint, we just pretend that every beam connected to it is being pulled apart, that it's in tension. Then we do the math. If our answer for a force comes out positive, hey, our guess was right, it's in tension. If the answer comes out negative, it just means the opposite is true. The beam is actually being squished, or it's in compression. The math literally tells you what's going on. No guesswork needed.
So we just repeat that process for each joint. It's a technique called the method of joints. And once we're done, we get to step 8, the final summary. We find out that member AB is being compressed with 500 newtons of force. Member BC is also in compression with 650 newtons. And member AC is being pulled apart. It's in tension with 400 newtons. And there you have it. That's the complete answer. A full picture of every single force keeping that thing standing.
Okay, so we solved one problem. Awesome. But here's the really cool part. The true power of this method is that it works for everything. This isn't just a how to solve a truss trick, it's a how to solve statics method. Let's take a look at how this same way of thinking can be used on totally different problems.
This is a perfect example. On one side, there's our truss. On the other, a totally different problem. A block on an incline. But think about it. How would you solve that friction problem? What's the very first thing you do? You draw a free body diagram of the block. You'd show its weight, the force from the ramp, the friction, and then you'd sum all the forces to zero. It's the exact same thought process.
And the pattern just keeps going. What if you need to find the center of gravity, the balancing point of some weird complex shape? Well, you use the same kind of thinking. You don't try to solve it all at once. You break that complicated shape down into simple pieces you already understand, like rectangles and triangles. Then you sum up their properties in a structured way to find the answer for the whole thing. It is the exact same fundamental idea. Turn complexity into simple, manageable pieces.
And really, that's the journey we've just taken, isn't it? We started with what looked like a really complex, maybe even intimidating engineering problem, and we ended up with a clear, logical, and repeatable path to the right answer.
So here's the main takeaway. The thing I really want you to remember. It's not about memorizing a few formulas. The real power is in having a solid, systematic process. It's more than just a calculation method. It's a tool for thinking. It's a way to build a path that you can trust to lead you to the right answer, even if you've never seen that exact problem before.
Because that skill, that ability to break down a big problem, define what you're doing, apply a set of rules, and then check your own work, that goes way beyond just engineering. That's the power of a systematic approach. So the question I'll leave you with is this: what complex problem are you going to solve next?